All right, so let's carry on with our discussion of astability and multi-step methods. Okay, so so if you recall, it's like the first thing we had checked really was that we wanted that the roots of some characteristic polynomial associated with the multi-step method had modulus less than 1 on the entire left half plane. Okay, and if you recall, it's like what we had done. It's like with the it's like astability analysis of Runge-Kutta methods, we were able to sort of relate that kind of result. It's like to sort of an easier result to verify, which just requires you to check basically the condition instead of the entire left half plane basically on the imaginary axis, and that involved an appeal, if you will. It's like to the maximum principle. So so let me say it's like sort of the analogous result now for multi-step methods. So let me state the lemma first. So the lemma is as follows, right? That the multi-step method just sort of remind you what it is, right? So the multi-step method is again the sum of am y n plus m, right? M goes from 0 to s is equal to h sum from m equals to 0 to s of bm f evaluated at y n plus m t n plus m, right, is astable, right, if and only if, right, bs is greater than 0, and sort of w1it all the way up to wqtit is less than or equal to 1, right, for t on the rails, right? So instead of checking a condition on the modulus of the of basically the roots of the some characteristic polynomial on the entire left half plane, you just have to check it on the imaginary axis, right? Okay, where again w1 to wqz are the roots of this characteristic polynomial. Okay, all right. And in some sense, it's like this, on the face of it, this is the sort of exact analog of the result we had. It's like for the Runge-Kutta case. What makes it a little bit more complicated is that this is not a complex plane, right? Because you are checking this condition simultaneously. It's like on, several roots, right? So this is some sort of S-sheeted Riemann surface, okay? So sort of, let me just sort of say the proof, right? So you might imagine, so this is not a direct application of the maximum principle, sort of the classic maximum principle. As the roots of this characteristic polynomial right, lives on a S-sheeted Riemann surface. Over the complexes. Okay, but you can still, there's still an analogous maximum principle, but you have to use somewhat more sophisticated machinery, right? So still has a maximum principal but sort of more sophisticated machinery is necessary. Okay. All right. Okay. So, but nevertheless, it's like you know, the result sort of is what you might expect from what you've seen, you know, with the Runge-Kutta case, right? So let me state a few more lemmas and theorems just to sort of close out this chapter on stiff problems. Okay, so this lemma it's like has to do with checking that condition. This is the Cohn-Schur criterion. Okay, so both zeros of the quadratic alpha w squared plus beta w plus gamma, where alpha, beta, gamma are in the complex plane, and alpha is not zero, right? Reside in the closed complex disk, closed complex unit disk. If and only if this condition is true, that modulus of alpha is greater than or equal to modulus of gamma, right? The modulus of the difference of the square moduluses is greater than or equal to alpha beta bar minus beta gamma bar, and alpha equals to gamma is not equal to 0. Implies beta is less than or equal to 2 modulus of alpha. Okay, so all right, so this is a criterion, if you will, it's like which you can use to check the conditions for A stability. It's like a multi-step methods. It's specific to this kind of quadratic equation, right? So it's not sort of extremely general. So this is a special case of a more general result, which is called the Cohn-Schur criterion. And this criterion is provides sort of a finite algorithm to check if all the roots of a polynomial, right, to any degree, has zeros which are in any closed unit disk in the complex plane. So basically, it's like you sort of take this more general result. It's like, and you specify it to the case. It's like where you just have a second-degree complex polynomial. It's like, and you've chosen a specific closed disk, which is just a closed unit disk in the complex plane. Okay, so the result itself is what it is. It's like the main reason it's like why I stated it's because it allows us to then say something about the astability of BDF2. Okay, so so let me state the theorem for BDF2. So the theorem is that well, BDF2 is astable, right? Two-step BDF method is astable. Okay, so the first thing you need to check is that, okay, so we have B2, it's like for the two-step BDF method is 2/3. So that's greater than 0, right? So that was one of the conditions we needed to check, which more or less, if you will, has to do with this analyticity result. And then the other thing you need to check is that the roots, it's like have modulus. The roots of the characteristic polynomial have modulus, which is less than or equal to 1, right? Okay, so so this characteristic polynomial looks like the following: 1 minus 2/3 z w squared minus 4/3 w plus 1/3. Okay, so you want to check the second condition, and all that is necessary, if you recall, is to check this for z, which is on the imaginary axis, right? So I can let z equals to I times t in the rails, right? Okay, so you can write down, it's like, okay, so I erased, unfortunately, this Cohn-Schur, it's like criterion, but the Cohn-Schur criterion, it's like was expressed in terms of the coefficients of the quadratic polynomial, right? So I'm going to substitute its z equals to it into this, and then get the coefficients of the polynomial. So alpha, of course, is just 1 minus 2/3 I times t, right? Beta is minus 4/3, and then gamma is equal to 1/3. Okay, so so that's of course just a quadratic polynomial. It's like there's some coefficients, and you can check that alpha squared minus gamma squared, right, is equal to 4/3 2 plus t squared, which is greater than 0, right? So that's one of the conditions which is satisfied. Okay, and then alpha squared minus gamma squared squared minus alpha beta bar minus beta gamma bar squared is equal to 16 over 81 t to the 4, which is also greater than or equal to 0. So the two conditions, it's like which you needed for it's like it's like the Cohn-Schur, it's like criterion to apply have been satisfied, and so so this implies that we have astability, right, of the sort of two-step BDF method. Okay, so that's the good news with BDF. Unfortunately, the rest of it is somewhat bad news. So only the sort of two-step BDF method out of basically the S-step BDF methods, where S is between 6 and 3, right? Well, including it's like 6 and 3, right? Well, I should say out of S between 2 and 6, right, is stable. Sorry, astable. And if you recall, it's like the reason why I don't talk about BDF methods which have more than 6 stages is because if they have more than 6 stages, they don't, they're not convergent, basically, right? Because they're not stable, actually, come to think of it, right? So if you don't have stability, it's like then you don't have convergence, right? So only S between 2 and 6, right? BDF are stable and hence convergent, right? So these really are the only BDF methods which matter. It's like at once, it's like which are between 2 and 6, including it's like 2 and 6. Okay, and of these, it's like, you know, convergent BDF methods, only the 2-step BDF method is astable. Okay, so this result, in some sense, is a consequence of an even more general statement about multi-step methods. Okay, so let me state a theorem. This is called the Dahlquist second barrier. Right, the highest order of an astable multi-step method is 2. Okay. So, and this is, if you will, it's like a consequence of this Werner-Hairer-Norset theorem. It's like which talks about Pade approximants being acceptable, right? So the remark is that this comes from condition, if you will, that r hat alpha beta is A acceptable, right, if and only if alpha is between, well, beta is between alpha and alpha plus 2. Okay? All right. So in looking at this result, you might think that this means that multi-step methods are, you know, never useful for stiff problems, and that's not strictly true. And the reason, if you will, is that you know, it's like the astability condition is in some sense extremely sort of rigid. It's a very strong condition, and for practical purposes, you don't necessarily need the full astability condition. So, so what do I mean by that? So what I mean by that is the following. So even though, for example, the 3-stage BDF method is not astable, its stability region does contain a very big part, if you will, of the complex, or the left half of the complex plane, just not the entire left half of the complex plane. So, so let me try to introduce, it's like this idea, right? So you can check that there exists some domain, let's call it V alpha, right, which is a set of rho e to the I theta, right, such that rho is greater than 0, and basically theta plus pi in absolute value is less than alpha. Okay, and this is of course contained in the complex plane, and so what essentially happens, if you will, is that you know, you don't quite have the entire complex plane. It's like, but you have basically a wedge, which is still pretty useful. Okay, and so, for example, and this is for alpha. It's like between 0 and pi. Okay. So you can check that the that sort of the three-stage, right, sorry, not three-stage, but three-step BDF method. Right, has a stability domain that contains sort of one of these V alphas, where alpha is 86 degrees, 2 minutes. Okay, so it's not the full, it's not the full left half plane. It's like what it would be if it was 90 degrees, but it's still a very large part of the left half plane, and so so these things are still useful for a large class of problems. All right, so so we say that a method is what we call a alpha stable, right, if instead of it containing the full left half plane, right, the stability domain D contains V alpha. Okay, and all the BDF methods, it's like which are relevant, which of course all the ones which are convergent are they're not A stable, but they're A alpha stable for some choice of alpha. Okay, so that's still useful for a certain class of problems, not for all possible problems, but that's still something which is a useful application, if you will, of these BDF methods. So I'll stop here.